So, organic chemistry. Much of what we will talk about for the next month is going to, and maybe 2 months, is going to be dominated by the chemistry of the carbonyl compound. So, behold, the carbonyl compound. R is generally an alkyl group or a benzene ring of some kind. Y can be any number of things. We're calling it Y because we're at BYU, and we'll say more specifically about it later. The carbonyl refers to the functional group carbon-oxygen double bond. Now, carbonyl reactivity is dominated by an important feature, and that is that the carbonyl can be both a nucleophile and an electrophile, and we need to explain and understand that. We're going to go more in depth than you wanted to do, and we're going to review some things from 351, and maybe you're going to learn some things you didn't know. It's going to be worth the time because it's going to help you do some things that are really key for you in organic chemistry. Really key for you, success in this class is number one, to be able to identify what about a molecule is important. Two, to focus in on that portion of the molecule. And three, to generalize what you've learned to other unfamiliar molecules. I can't count the number of times students have looked at a molecule that was large and complicated and said, I don't know what to do with that. And then I said, well, just focus in on this part. And then they're like, oh, okay. My goal is for you to get to the point where you don't need to come to me to ask me what part you should focus in on, but rather have that skill yourself. So let's learn to do that with the carbonyl. There's two ways to understand carbonyl chemistry. Both of them are valuable. I'm going to show you both of them. The first one is easier, and that is to use the concept of resonance. You should be familiar with the concept of resonance, and you should understand how I'm drawing a resonance structure of the carbonyl compound in which I have moved the electrons, the pi electrons from the carbon-oxygen pi bond out onto the carbonyl oxygen. Okay? And you should understand that in resonance, we don't actually mean those two electrons are hopping back and forth between the oxygen and the carbon now on the oxygen, but rather that each structure is an incomplete description of the molecule. You learn from these resonance structures that the carbonyl carbon is electron poor. That in the true structure of this molecule, there should be a partial positive charge on the carbonyl carbon. Does that sound familiar? Yes. If it doesn't, you better say something because we're okay. Yeah, go ahead. That's right, yeah. The other important feature, yes, is that oxygen, and the one thing that makes this resonance structure reasonable that you should remember, and that's going to come up again in a number of contexts, is oxygen is more electronegative than carbon. We'll say more about electronegativity in a minute. I know what you think electronegativity means. You think electronegativity means the atom likes electrons and pulls on them more. Not quite that, but we'll say a little bit more about it later. But for right now, it's enough to know that oxygen's more electronegative than carbon. So you expect the carbonyl carbon to be electron poor, and you expect the carbonyl oxygen to be electron rich. Okay, why are we bothering with that? Well, because you learned in 351 that the first and great commandment of OChem is that nucleophiles attack electrophiles. And nucleophiles are molecules that are electron rich. Electrophiles are molecules that are electron poor. Therefore, it is useful to be able to look at the structure of an organic molecule and identify what portions of the structure are electron rich and are therefore likely to be nucleophilic versus what portions are electron poor and are therefore likely to be electrophilic. All right, so we will see that one key feature of carbonyl compounds is they can be both nucleophiles and electrophiles. Excuse me. If they're nucleophiles, we expect them to be reactive at the carbonyl oxygen because that's the electron-rich portion of the molecule. If they're electrophiles, we expect them to be electrophilic at the carbonyl carbon because that's where they're electron poor. All right? Now, I'm going to do something that I didn't do in the 9 o'clock lecture because I think it'll work a little bit better. If I were to have a nucleophile and it were going to attack the carbonyl compound as an electrophile, where should I draw my arrow from the nucleophile? To where? To the carbonyl carbon, right? Okay. I'm going to just, it doesn't matter which resonance structure I choose. I'm going to choose the one on the right. What does that arrow mean when the nucleophile attacks the carbonyl carbon? What does that arrow mean? What's going to happen? Go ahead.
The electrons from the nucleophile are going to attack the carbon to form a bond.
Yeah, you're going to form a new bond. The arrow is literally the instructions for drawing the next structure. It should involve a new bond, right? So we could actually draw that structure right now, and here's what it would look like. With a new bond in red to the nucleophile. What if, now because I chose the resonance structure on the right, we were able to draw that structure pretty directly, but both resonance structures are correct, so there should be a way for me to draw this same set of arrows here. What's the problem with just doing that? Go ahead. 5 bonds to carbon, you broke the octet rule. Texas carbon, right? All carbons have 4 bonds, even in Texas, right? So, right, so what do we have to do? We have to break the carbon-oxygen pi bond, and it makes sense that the electrons in the carbon-oxygen pi bond should go to the oxygen, which is more electronegative. So those are two equivalent ways, both are fine, of showing a nucleophile attack an electrophile, attack a carbonyl compound as an electrophile. Either way, you make a new pi bond, a new sigma bond between the nucleophile and the carbonyl carbon, and a lone pair from the carbon-oxygen pi bond ends up on the oxygen. And we call that intermediate a tetrahedral intermediate. All right, questions about that so far? Now, we want to go one level deeper into the area of molecular orbitals because this will help you understand a few important features of carbonyl chemistry that might be difficult to remember otherwise. In particular, what we're going to talk about now answers the question, why does this bond have to break? Okay? So before we do that, we're going to go, we need to do a little bit of review from 351 about bonds and orbitals. And because I didn't teach you in 351, I'm not sure what you've learned about this. Most of my colleagues teach some amount of this area, but we each do it a little bit differently. So just work with me, and if you got it all, we'll move pretty quickly through this. Let's start with, we'll have an energy sort of diagram. This arrow and this axis represents energy. Lower energy, more stable towards the bottom. Higher energy, less stable towards the top. And we're going to rank bonds and orbitals here. Okay, so tell me what you know about a sigma bond versus a pi bond. A sigma bond is higher or lower in energy than a pi bond. Okay, I heard two things, higher or lower. I'm not sure what we're talking about. So let's rank them. I'm going to put two lines here. Which one should be sigma? It's true that sigma bonds are lower in energy than pi bonds. Now, why is that? Go ahead. Okay, so it's lower in energy because it's more stable. Those are actually two ways of saying the same thing. Why is it more stable? Yes?
It's
closer to the nucleus. Good. So a sigma bond, if you were to draw what a sigma bond looks like, I'm just going to draw for you, well, since we're dealing with carbonyls, maybe, a carbon-oxygen sigma bond we would get from overlap of an sp3 orbital on carbon with an sp3 orbital on oxygen, or an sp2 orbital, some kind of hybridized orbital, to make a sigma bonding orbital, which is in the end going to look like this. Most of the electron density in the sigma bonding orbital is going to be held in between the two nuclei. Before we get to the pi bond, I have to say something about orbitals. You've seen p orbitals and sp3 orbitals before. You've seen people use shading. Here is a p orbital, and you've seen people do things like this where they color one side one color and the other side the other color. What the heck does that mean? Can we say heck here? Yeah, we can say heck here. What does that mean? Any ideas? Yes? Electrons are in opposite spins. Close. It's not actually spin, but it does have to do something with the electrons. Others? Any? Okay. Yeah.
Is it in phase versus out of phase?
In phase versus out of phase. Yeah, what do you mean by phase?
I'm not entirely sure.
Good, me neither. Yeah, so the best way to understand it is this. It does have to do with phase. Think of just a sine wave on that you drew in junior high. A sine wave can have positive magnitude or negative magnitude, or it can be zero, right? In the same way, an electron in an orbital, the orbital is the electron wave function. It is the wave form adopted by the electron. And just like a sine wave, that electron can have positive magnitude or negative magnitude. Now, it has nothing to do with charge or spin. Spin is actually a separate property that actually is also involved in wave function. But we get sometimes confused with the plus and minus magnitude and positive and negative charge, or maybe upspin and downspin. So to avoid all of that confusion, generally chemists use color and shading to indicate areas of the wave function that have opposite sign. And we don't care which one is positive and which one is negative, just that they have opposite sign. Okay? So we will use the sign of the wave function as a way to keep track of what kind of orbital that we're dealing with. The other thing is that the sign of the wave function can give you some really interesting insights into how individual orbitals interact with each other. For example, if I took the, let's say in red, this sine wave, and I added it to another sine wave, and they overlapped with the exact same wave function sign, the sum of that would be what? It should be higher, right? We draw something like this, right? In contrast, if I added this sine wave to, oh, let's see if I can do this one, what would happen? They would tend to cancel each other out, just like mathematical quantities. And this is the constructive versus destructive interference that you were talking about. So we will use the phase, or we'll use the term phase to describe the sign of the wave function. We're going to use that quite a bit in thinking about orbitals. Notice that bonding orbitals come when individual atomic orbitals overlap with each other side by side with the right wave function sign. So we could draw a pi bonding orbital, or the carbon-oxygen pi bonding orbital we would get by having a p orbital on carbon and a p orbital on oxygen overlap with each other side by side with the same wave function sign, such that there would be constructive interference when they got close to each other. And in fact, what you would actually look at, what you would see in a carbon-oxygen pi bonding orbital would look like this. And maybe this is the familiar form of a pi bonding orbital that you've seen before, with a lobe of electron density above and below the line between the two atoms. Does that look familiar for a pi bond? Okay. Maybe a little bit of perspective is useful. I'm going to draw the rest of the carbonyl compound here, just so that you can see it. Here's the Y group. Here's the R group. All of those bonds, carbon R, carbon Y, and carbon O, are in this gray plane that I will draw. The pink lobe is above the plane. The yellow lobe is below the plane. Okay? That's what a pi bond looks like. And in fact, and that's actually what a pi bond would look like if it were a carbon-carbon pi bond. It turns out because oxygen and carbon don't have the same electronegativity, that the orbital looks a little bit different than that. So we need to correct this drawing a little bit. Oxygen is more electronegative than carbon. What that literally means is that electrons are lower in energy or more stable on oxygen than they are on carbon, which means electrons in this pi bonding orbital are going to lean towards the oxygen. So if we were to draw this how it actually appears, what it would look like is the orbital is leaning towards the oxygen, kind of like this. You guys are probably too young to have watched the 1990s Christmas classic While You Were Sleeping. No, where Joe Jr. explains, "Yo, Luce, is this guy bothering you? Because he looks like he's leaning." Anyway, you should go watch it. It's kind of funny. That's a dated movie reference, but it's worth your time. In any case, the pi, what we learn is that the electrons in the pi bond are leaning towards the oxygen. Now that tells us exactly what we learned before from resonance, that the oxygen is electron rich. Okay? Now, second thing we need to do, I'm just going to redraw the carbonyl compound up here. We've dealt with sigma bonds and pi bonds. I'm going to just draw little blue lines to indicate there's multiple sigma bonding orbitals. We're not going to draw them all. They're all about the same energy. So we're going to be general and say there's multiple sigma bonding orbitals. There's one pi bond. There's a couple of lone pairs on the oxygen. How do lone pairs rank in energy relative to pi bonds? Higher or lower? Higher. How do you know that? Because they're not involved in bonds. Bonding is what moves electrons down in energy. They get to be between two nuclei. That's a potential energy argument. And then they get to spread out in space. That's also stabilizing. That's a kinetic energy argument, but we won't talk about that in any detail. So electrons that aren't involved in bonds, electrons that are localized on individual atoms, are always higher in energy than electrons that are in bonds. So we're going to find lone pairs are higher in energy than, for carbonyl compounds, than are the sigma or pi bonding orbitals. Okay? And those lone pairs you can just think of as electrons on the oxygen. Again, now looking at this list, and that accounts for all of the electrons in this molecule, electrons in sigma bonds, electrons in pi bonds, and electrons in lone pairs. Which are the most reactive electrons in this molecule? Where are they? Lone pairs. So if the molecule is going to act as a nucleophile and attack with its high energy electrons, the things that are going to do the attacking are these ones, the lone pairs. That is why you always focus, when a carbonyl compound is a nucleophile, you always focus on the oxygen lone pairs as being the nucleophile. Okay? This is how we focus in on what's important. Now, all of this maybe is review. There's a concept you maybe had and you maybe didn't have in 351, and that is the concept of an anti-bonding orbital. Just to clarify, the sigma and pi bonds are bonding orbitals. The lone pair is a non-bonding orbital. But up here we have things that are called anti-bonding orbitals. Some of you may have talked about this a lot, others maybe didn't. Go ahead. Sure, there are two lone pairs in the oxygen. So we could draw two of them, yeah. I was going to not do that in the same way that I didn't draw one for all the sigma bonds, but it's fine. Yeah. Okay. Now, what is an antibonding orbital? It turns out every bonding orbital also has a corresponding empty antibonding orbital. We distinguish them from their corresponding bonding orbital with the addition of a star. So there's going to be associated with every pi bonding orbital, there's going to be a pi star antibonding orbital. Associated with every sigma bonding orbital, there's going to be a sigma star antibonding orbital. If that's unfamiliar, or if you want to learn about it in more detail, there's a totally optional molecular orbital theory study guide available on the content page of Learning Suite. It's excessively long because it's what I use for 351. Not all of my colleagues go into that much detail, and it's fine if you don't want to, but if you want to know more, you can go learn more there. Basically, antibonding orbitals come from the out of phase or opposite in wave function sign combination of the two atomic orbitals. Remember, we said a pi bond comes from having two p orbitals adjacent to each other side by side with the same wave function sign. The pi star antibonding orbital comes by having those two side by side but with opposite wave function sign. So we can draw, for example, a pi star antibonding orbital like this. Here's the carbon, here's the oxygen. And at least conceptually to begin with, let's start with a p orbital on carbon and a p orbital on oxygen. But they're going to come together side by side, but there's going to be a switch in wave function sign as we go from left to right. That is, the wave function sign is going to have, let's say, positive magnitude here. It's going to go through 0 in between and then have negative magnitude over here. Or negative magnitude here, and as we go to the right, go through 0 and positive magnitude. In other words, there's destructive interference because they've come together side by side out of phase. They cancel each other out in the middle. The place where they cancel each other out is called a node, and that is a place where no electron density can be. If electrons were in this orbital, they wouldn't spend any time between the two nuclei, and that's why it's called an antibonding orbital. There's no bonding stabilization. For reasons we don't need to talk about in detail, the antibonding orbitals rank in energy exactly opposite the bonding orbitals. So just as the pi bonding orbital is higher in energy than the sigma bonding orbital, so the pi star antibonding orbital is lower in energy than the sigma star antibonding orbital. If you want to know more about sigma stars and what they look like, we don't need to talk about that today, but you can look in that molecular orbital theory optional study guide. Okay, questions so far? We still haven't gotten to the therefore what. Go ahead.
Why is the anti-pi higher in energy than the lone pair?
Why is the antibonding pi orbital higher in energy than the lone pair? Because what that tells you is the antibonding orbitals are destabilized relative to atomic orbitals. And that is because there is an explanation for that. It's probably beyond the scope of this class. Though, if you want to know, it has to do with the kinetic energy of the electrons and how fast the wave function sign is changing. Everybody plug your ears, you don't want to know this. But the kinetic energy of a wave function is related to the second derivative of the wave function with respect to space. That's curvature. The more the wave function changes, I told you you didn't want to know. The more the wave function changes, the higher in energy it is. And so antibonding orbitals have nodes. The wave function has to change a lot to go through 0 to get through that node, and so it's higher in kinetic energy. You can look more at that study guide if you want to know more. It's really awesome. You should really want to know more, but I know you don't. Okay, other questions? Yeah?
If you filled the anti-bonding orbitals, wouldn't that break the bond?
Good, excellent point. If you fill the antibonding orbital, you would break the bond. Absolutely. And you may have learned this just briefly in either general chemistry or 351. If you think about hydrogen, hydrogen has 2 electrons in a sigma bond, and that sigma bonding orbital is here in energy. It's lower in energy than sort of this starting place where an atomic 1s orbital would be. And then up here is the sigma star antibonding orbital. Of course, in hydrogen, you've got 2 electrons in that bonding orbital. If you could promote one of those electrons with light or some energy to the higher antibonding orbital, you would totally cancel out the stabilization of the bond, and the bond would break. And we see this in general, that if you fill an antibonding orbital, the corresponding bond breaks. And that's really important. And we're going to go there with the pi and the pi star in just a second. Before we do, there's one more thing I need to say about the pi star, because its shape is not exactly like this. The effect of oxygen's electronegativity has an effect on the pi star just as it did on the shape of the pi orbital. So if I were to draw sort of the way I did below here, a carbonyl on its side, and here is the plane that the carbonyl lies in the same way that the filled pi bonding orbital is leaning or polarized towards the oxygen, so the empty antibonding orbital is actually polarized towards and leaning towards the carbon. In other words, more of the pi star is on the carbon than on the oxygen. It's the same reason for the effect. Oxygen's electronegativity pulls the bonding orbital towards it, and as a result, the antibonding orbital has to lean correspondingly towards carbon. In blue is the node. Let's see, in gray here is the plane of the page. What's here is above the plane, what's here is below the plane. Okay? So a key thing about carbon-oxygen pi stars is that more of the carbon-oxygen pi star, we might even say most of it, is on the carbonyl carbon. Now that tells us, well, before I say that, think about the carbonyl as an electrophile. When a nucleophile attacks electrophiles, a nucleophile has to have a place. The electrophile has to have a place to put the electrons from the nucleophile. That's the simple concept of Lewis acid and Lewis base. Lewis base nucleophile attacks Lewis acid. You have to have an empty orbital on the Lewis acid or the electrophile to accept the electrons. For the carbonyl, the lowest energy empty orbital is the pi star. That is the place the nucleophile will attack. And as I just showed you, most of that pi star is on the carbon. So, again, skill. Focus on what's important about the molecule. Know what's important. If the carbonyl is the electrophile, what's the important part of the molecule? It's the carbonyl carbon. That's where the nucleophile is going to attack. And then the fact that what we just said about antibonding orbitals when they're filled breaking the corresponding pi bond tells us why this second arrow has to happen. What I'm showing you here is that the nucleophile is dumping its electron density into the pi star at the carbonyl carbon. That does two things. It makes a new carbon, it makes a new nucleophile bond, and it breaks the pi bond. And we can even draw this orbital picture superimposed here on this structure. If we were looking down, it'd be like we were hovering here over the plane and looking down on the molecule from above. There would be a large lobe on the carbonyl carbon, a smaller lobe on the oxygen, a node in between. We'll make this one pink and then this one orange, and then below the plane of the page there would be other lobes that we can't totally see, but I'm just going to give you a hint of there and there. So when the nucleophile attacks the pi star, it does so at the carbonyl carbon because that's where the pi star mostly is, and then the second arrow is the pi bond's got to break. Okay? Yeah?
Did you draw the lobes with the colors being on opposite sides because there's destructive interference? The bond is breaking?
Did I draw the lobes on opposite sides with opposite colors because they're destructive interference? Yes, that is what an antibonding orbital is. You'll be able to identify antibonding orbitals because they will have a node in between the two nuclei, which tells you that it's an antibond, that there's no, if it were a bond, there would be no node, there would be constructive interference, which is what you see for the pi star. Okay, good. Others? Yes?
So like, going to what you just explained, there would be almost like three phases of orbital changes, right? So what we call like electrons in the antibonding pi to then electrons in the lone pair, and then so like lone pair and a sigma. So there would be two new orbitals.
That's right. I think, let me just repeat the question. The question was, So if you understand the reaction correctly, lone pair on the nucleophile becomes a new sigma bond by dumping its electrons into the pi star.
First go into the antibody.
Right, yeah, first goes into the pi star. That makes the new sigma bond between carbonyl carbon and the nucleophile. Then, because you've filled the pi star, the pi bond's got to break. The electrons in that pi bond have to now become a lone pair on the oxygen.
And
Yep.
the other one is more preferable because there's three, you now have like 4 sigma bonds.
Right, so is it preferable to do this? We haven't talked yet about reactivity. All we've talked about yet so far is mechanism and what's happening. We haven't necessarily yet talked about why or whether it's favorable, but we're going to do that. And whether or not it's favorable is going to depend, as you said, on the strength of this new bond between nucleophile and carbonyl carbon. But it's also going to depend on this Y group for reasons that we're going to talk about now. But before we do, what else? Yeah.
Why does the lone pair fill the anti-orbital if that's higher?
The lone pair from the nucleophile attacks the empty orbital because that's the only empty place to go. There's no other holes to fall into. Yep. All right. Good. Well, we need to now focus in on this Y group and its impact on the reactivity of the carbonyl compound. And the question we want to ask, there are 2 questions we want to ask that are going to help us understand how this Y group impacts carbonyl reactivity. The first question we want to ask is Y a good leaving group? Now, right now, it's not apparent at all why on earth we should be talking about why the Y group is a good leaving group or not. That'll become clear, maybe not by the end of today, but certainly by next time. And then we'll be off to the races with new reactions. A second and related question is the Y group a good electron donor? You're going to see that these are actually the same question. But let me give you some examples of what the Y group can be. This won't be a complete exhaustive list, and we won't finish it really today. But let me give you some examples of good leaving groups. And we'll rank these from good to less good. And before we get too far onto this, I always want you to be thinking in the back of your mind, good relative to what? I'm not answering that question today, but we will answer it. And the relative to what questions are really important in terms of predicting what's going to happen in an organic molecule. So more good to less good. So let's just think of some things that could be good versus less good leaving groups. We'll start with Cl minus. And here is a place where if it's been a while for you for 351, you may want to take a moment and go back and review some pKa stuff from chapter 2. Cl minus, as you learned in 351, is a good leaving group. One of the ways you can tell is by drawing its conjugate acid and noticing that the conjugate acid of Cl minus is actually a really strong acid. HCl has a pKa of around -7. Remember, the lower the pKa, the stronger the acid. Remember that strong acids are strong because their conjugate bases are really stable with electrons. Really stable conjugate bases make excellent leaving groups. It's all coming back to you now, you and Celine Dion, good. That was a new one. I didn't try that one in the 9 o'clock hour, so maybe I'll work that in next time. Let's see, so also a good leaving group would be H2O. I guess, let's see, because its conjugate acid is H3O plus, except I'm making up molecules now, did that at 9 too. Oh, well, pKa is -2. An alcohol could be a good leaving group as well, that are OH. Oh man, I'm struggling today. What's going on there? protonated alcohol or oxonium ions have pKa's around -2. Those are good leaving groups. Also that we will encounter are carboxylates. They are conjugate bases of carboxylic acids, which have pKa's of 4. Decent leaving group. One that may be unfamiliar to you, but that you will encounter in 352 is the thiolate. It's a negatively charged sulfur. It's the conjugate base of a thiol, which has a pKa of around 8. All of these are decent leaving groups. One that's important in biology, but that you might not have encountered in 351 is a phosphate group. These are annoying because, as you know, phosphoric acid is one of these polyprotic acids that you hated from general chemistry. I'm drawing you the dianion, the monohydrogen phosphate. Its conjugate acid looks like this and has 2 hydrogens on it and still 1 negative charge. That pKa is around 7, around physiological pH, so that's actually a decent leaving group. And so we can rank others as well, for example, NH3 or some kind of amine have positively charged conjugate acids that are called ammonium ions. These can be good leaving groups. They have pKa's in the 9 to 11 range. Generally, the place where we're going to start calling leaving groups poor is where we get to things like OH minus, which that shouldn't be a surprise to you. OH minus hydroxide or OR minus alkoxide is a not great leaving group. The whole theme of chapter 9 of 351 was that OH minus is a bad leaving group. So if you want to do chemistry with alcohol, substitution or elimination chemistry, you often have to turn the OH into a good leaving group first, right? That's going to be a theme for us too. OH minus, OR minus are generally poor leaving groups. Conjugate acids, alcohols, waters have pKa's around 16. So we might continue, and I don't need to belabor the point, but we're ranking leaving group goodness basically using pKa information that's old. Now you don't have to have these memorized. There'll be a pKa table for you available on the exam. But, yay. I mean, except for the -2 and the 16 one. That one everybody knows and you should have memorized, right? Yes?
It's not on the ACS.
No, the ACS, you don't get any resources for that. It's just you, your brain, and a piece of paper and a pencil. But again, don't worry about it. There's reasons for that. I'll address it in the future. For now, it's a long time away, so don't worry about it. Right. So let me tell you why. Well, so we've talked about what are good leaving groups. It turns out the question is why a good electron donor or not is exactly the same as whether or not it's a good leaving group. The worst leaving groups are the better donors. The best leaving groups are the poorer electron donors. I'm going to add real briefly to this list the negatively charged nitrogen, whose conjugate acid is ammonia, the neutral amine, who has a pKa of like 38. That's a terrible leaving group, but a very good donor. Now let me try to illustrate why we care, okay? And we won't get to the end of this, but I want you to compare in reactivity this ester versus this new functional group called the acid chloride. And we want to determine which of these two is the better electrophile. We're going to focus in on the identity of that Y group as a donor. You know that, so what is the Y group here? The Y group would be methoxide, or over here would be chloride. Methoxide is a good donor. Cl minus is a poor donor. Why do we care about that? Let's draw the resonance structure of the ester. Let's draw the one in which there's a positive charge on the carbonyl carbon and a negative charge on the carbonyl oxygen. And then let's notice that that methoxy Y group has a lone pair on the atom that's adjacent to the atom that's positively charged. So I should be able to draw a resonance structure in which that lone pair donates into the carbonyl carbon to make this resonance structure in which the lone pair is now a pi bond between the oxygen and the carbonyl carbon. The effect of having a good donor on a Y group is to stabilize or spread out the positive charge on the carbonyl carbon and thereby make it less electrophilic. Having a good donating group at the Y position makes the molecule less electrophilic. Now, chloro is not a good donor, so you tell me now, who's more electrophilic, the ester or the acid chloride? Acid chloride. Why? Because it doesn't have as good of a donating group, doesn't stabilize the positive charge on the carbonyl carbon, so the carbonyl carbon's more electrophilic. Okay, we'll pick this up again tomorrow, now on Friday, and do more things. Get started on those study guides, and we'll see you then.